Chances are you've already used ChatGPT or some other language model today, but have you ever stopped to wonder how they actually process human language? Well, welcome to The Explainer. Today, we are pulling back the curtain on the incredible engine that powers modern artificial intelligence. We hear a lot of buzzwords about deep learning and massive models, but how do they actually learn? We're going to break down the exact mechanics, starting from the absolute smallest mathematical components and scaling all the way up to text prediction. Okay, let's dive into this.
Think about this for a second. Way back in 1948, Alan Turing already saw the vision. The underlying secret of neural networks isn't that they're made of impossibly complex, magical algorithms. Not at all. It's actually that incredibly simple, almost rudimentary individual units can scale up to perform massive, profoundly complex tasks when they are networked together. It's a perfect micro-to-macro story. So here's our roadmap for this explainer. First, we'll meet the single neural unit. Then we'll tackle the historical XOR problem, build feed-forward networks, figure out how to process human language with embeddings, and finally, watch the network actually learn from its mistakes.
Let's start with Section 1. Meet the neural unit.
I know, the math looks like intimidating calculus, but it honestly translates into three highly intuitive procedural actions. Think of a single neural unit as a tiny, isolated decision maker. First, it just takes a list of input values. We call that a vector. Second, it multiplies each input by a weight and adds a bias. And you can just think of a weight as the importance of an input. It's asking, is this input absolutely crucial or is it barely relevant? The bias is simply the unit's baseline tendency, kind of like its starting point before any evidence is even weighed. It takes all of this and adds it up into a single weighted sum. But to actually be useful, it needs one final step.
It has to pass that sum through what's called an activation function. These are nonlinear functions, and they are absolutely vital. A really popular one is the sigmoid function, which elegantly squashes extreme outliers into a neat, tidy range between 0 and 1. Another one is ReLU. Honestly, think of ReLU like a bouncer at a club. If your value is positive, come on in. If it's negative, you get a 0. Done. Why do we need this? Because without these nonlinear transformations, stacking units together would just collapse into one basic, flat linear equation. We would completely lose all the network's power to represent the complex, messy data of the real world. Moving on to Section 2, solving the XOR problem. So historically, a single unit, which was called the perceptron, could easily be programmed with basic weights to solve simple logic problems like AND or OR. For example, it can effortlessly draw a line separating cases where both inputs are 1 from the rest. But then we hit XOR, or exclusive OR. It's a lot trickier. Here the output is 1 only if one input is 1 and the other is 0. If both are 1 or if both are 0, the output is 0. Now back in 1969, researchers mathematically proved a single unit could never solve this.
Now you might be wondering, why can't a single neural unit figure this out? Why can it easily solve AND logic but completely fail at XOR logic? Believe it or not, this one little math puzzle essentially brought research to a grinding halt for years, causing a massive AI winter where funding just completely dried up.
The answer actually lies in geometry. A single unit acts as a linear classifier. It makes its decisions by drawing a single, perfectly straight line right across a space. But XOR is what we call not linearly separable. If you were to plot the positive and negative cases of XOR on a grid, they sit diagonal from one another. It is physically impossible to draw just one straight line that puts all the positives on one side and the negatives on the other. You would need a curve, or multiple lines to do that. Basically, a single unit is completely trapped by its own linearity.
Let's move to Section 3, building feed-forward networks, and see how this builds to solve that exact limitation. The ultimate solution to the XOR problem was teaming these units up into multiple layers. Let's contrast two approaches here. On one side, we have logistic regression, which is essentially a one-layer network. Now, for this to work well, humans have to painstakingly hand-build feature templates based on their domain knowledge. It's a lot of manual work. But on the other side, we have deep neural networks. By stacking units in multiple layers, the network doesn't rely on us to hand-feed it perfectly engineered features anymore. It literally induces and learns its own feature representations straight from the raw data.
The absolute key to this is the hidden layer. By adding a fully connected intermediate layer of units right between the input and the output, the network can actually merge and transform the inputs.
In the case of our tricky XOR problem, the hidden layer actually merges the two positive data points into a single point in a new hidden space. And suddenly, boom, you can draw a straight line through it. The network basically changes the shape of the problem until it can solve it. This is the superpower of representation learning. And this exact superpower is how modern AI eventually learns to understand abstract concepts like human speech or images.
All right, Section 4. Processing language with embeddings. Let's see this super team in action.
So how on earth do we feed a human word like dessert into a math equation? We start with what's called a one-hot vector. Just imagine a massive list of literally every word in our vocabulary. A one-hot vector is just a giant string of zeros, with a single one sitting exactly at the index position of our specific word. We then multiply this one-hot vector by a massive, static dictionary that we call an embedding matrix. Because the vector is entirely zeros except for that single one, this math operation cleanly slices out a dense mathematical representation, an embedding, for just that single word.
But obviously, sentences have multiple words, right? So how do we handle a whole window of text? Well, there are two main strategies. First is mean pooling. This simply averages all the word embeddings together into one single vector. This is fantastic for sentiment analysis. Think about it. If a sentence has the words great, excellent, and delicious, the exact order doesn't really matter for us to know the review is positive. But if we want to predict the exact next word in a sentence, order is absolutely everything. The dog chased the cat is completely different from the cat chased the dog. So for this, we use concatenating. We physically link the word embeddings sequentially into one very long vector, preserving the exact order before we pass it into our hidden layers.
Finally, Section 5, Training the Network. This is where we see it learn.
So how does it get better? It learns by realizing exactly how wrong it is. We measure this using something called cross-entropy loss, which is also known as negative log likelihood. Look, a perfect classifier would predict the correct word with 100% probability and have zero loss. But early on, the network predicts very poorly. So the crucial point is this. Because all the predicted probabilities across the entire vocabulary absolutely must sum to 100%, maximizing the probability of the correct answer automatically forces all the incorrect probabilities down. It's an incredibly beautiful, unified metric for calculating error. And this creates a continuous, ongoing optimization loop. First comes the forward pass. The network pushes the inputs through all its random weights and spits out a prediction. Next, we calculate loss, measuring exactly how far off that prediction is from the true answer. Then comes the real magic, the backward pass. We take that exact error signal and propagate it backwards through the network, tweaking every single weight and bias just slightly, so that next time, the prediction will be a little bit better. This backward pass is called error backpropagation. Think of the entire network as a vast computation graph. Backpropagation basically applies the chain rule from calculus. It transmits the error signals from right to left, moving from the final output loss upstream back to the very first layers. And hey, remember those activation functions from the beginning? If we use the sigmoid function in deep networks, the error signals, the gradients, would get smaller and smaller as they passed back, eventually just stalling out completely. This is the infamous vanishing gradient problem. But by using the ReLU activation function, which has a clean, constant derivative for positive numbers, the math keeps flowing, and even the deepest layers can still learn effectively. Which brings us to our final thought. Let's recap. We started with one simple mathematical unit adding up weights. We grouped them into hidden layers to solve complex logic like XOR. We fed them embeddings of human language, and we used backpropagation to minimize their errors. So, if feeding forward and propagating back can teach a small machine to accurately predict the next word in a sentence, what happens when we scale this exact same foundational math up to billions of parameters? That right there is the threshold of the modern era of large language models. I really hope this explainer gave you a deeper understanding of the gears turning inside modern AI. Thanks for joining me, and keep learning.